Suppose I want to effect the following transformation. I want to take isopropyl benzene and make 2-isopropyl aniline out of it. How might I do this? Guaranteeing that my new substituent, the amine, goes on the position I want it to. In this video, I'm going to introduce the concept of blocking groups. Blocking groups. We really have two that we can work with. And we're going to see that blocking groups are something that we can put on to kind of prevent a position from being attacked, to kind of block off a position on the benzene. And very importantly, it must be removable. Because if we wanted to just block a position, but we don't want it there in the final product, we have to be able to take it off. And so, when we think about this, if we want to put an amine there, normally we look at isopropyl benzene, aha, ortho-para-director. Pretty bulky group, it's going to direct things para to itself. But the product I want is ortho. So this is a great time to use a blocking group. So what we're going to do is we're going to use a substituent that we can take off later. We're going to put that substituent in the para position. And once it's in the para position, the only place left is ortho. And then we can go ahead and put our amine on, and then we can get rid of that blocking group. And so we have really two options of blocking groups here. Most commonly is our dear friend, the sulfonic acid. We can put it on using fuming sulfuric acid. We can take it off using dilute sulfuric acid. Another option, though, is a nitro. And nitro has very kind of more specific utility, because we can actually turn it into an amine, which we then turn into, I guess we need to put that as an NH2. We'll turn that into a diazonium, which then we can turn into a hydrogen, back to nothing. Remember, so it's a little bit more complicated, but the difference here is, as we'll see, sulfonic acid is a moderate deactivator. A nitro group is a strong deactivator. An amine is a strong activator, and all we did not cover it necessarily, a diazonium is a strong deactivator as well. Although, again, it's not really common that we use that as an activating thing, because usually we just go ahead and throw whatever we're trying to put on. Remember the diazonium, the Sandmeyer reactions, we usually just use those as a stepping stone to get something to something else, but technically speaking, diazoniums are strong deactivators because they have that positive nitrogen right next to the ring. So depending on what we may need, if we need a strong activator, it may be a good idea to go to that amine and then diazonium route. Or if we need if we don't need that, we should probably just use the sulfonic acid, because that otherwise we're going to add way too many steps to our process. Remember that synthetic efficiency is all about minimizing extra steps. So the fewer steps you can do a synthesis, the better. So I think in this case, because we already have our substituent, the amine is going to be already ortho to an ortho director, we don't need to use the nitro route. So let's go with the sulfonic acid. And so if we want to accomplish that, we're going to want to put on that sulfonic acid, block off that para position, then go ahead and put the amine on, and then we can take off the sulfonic acid. And of course, thankfully with this, there's also some flexibility as to what steps you want to do when. Maybe we put the nitro on and we don't reduce it right away. Maybe we put the nitro on, then use the sulfuric acid, the dilute sulfuric acid to get rid of the sulfonyl, and then we reduce it to the amine. Doesn't matter. And that's, again, the beauty of this is there's a lot of freedom. So what we should do is put on our blocking group. If we do that, put our fuming sulfuric acid in here, we're going to get that onto the para position, right? both the sulfonic acid and isopropyl group are bulky. Sterically, it's going to drive towards para. Now, if we go ahead and nitrate it, using our nitric acid and concentrated sulfuric acid, now we're going to put the nitro group ortho to our strongest, I guess I could say, it's guided by our strongest activator, which is the isopropyl group, so it's going to go ortho to the isopropyl group. And the next two steps can be done in either order. We can reduce the nitro to the amine, or we can get rid of the sulfonic acid. Again, it does not matter in this particular problem. So let's go ahead and, I'm going to go ahead and use iron and HCl here, and I'm going to go ahead and reduce that amine down, second NaOH. Now remember, you can use iron or zinc here, and you're going to go ahead and reduce a nitro group to an amine. So we'll have our sulfonic acid, and now we have our amine, and then dilute sulfuric acid will take off our other group. So we now have an H there, which is what we wanted, right? We don't want anything special, we just wanted a hydrogen, and now we have our ideal happy compound. Ta-da! So blocking groups are very useful, synthetically speaking. It does add a few steps, but it eliminates side products, and that's preferable, right? So if half your product or 2/3 of your product is going in the trash, that's worse than adding a few extra steps, right? If you're just trying to separate, I only want the ortho product, I don't want the para one, better to just block off that para position. And thankfully with the sulfonic acid, it will always go para. So it's how you'll block off the para position, because otherwise your nitro will go to the para position. If that's where you want it, that's great. So no problems there. And so blocking groups are synthetic tools that we can use in our synthetic schemes towards making sure that our new substituents go where we want them to go. And so I would suggest that it'd be a good idea to identify when you'll need them. You just take a look at a few benzenes, think when you might need a blocking group. And typically that's when you have a lot of substituents together on one side of the molecule. Like in this one, we had both the isopropyl and amine very close to each other, so probably a blocking group was used during this. And so blocking groups, great way to use in your synthesis to make sure that you're guiding your position substituents to the right positions. In our next video, we'll actually take a look at several synthetic examples.